Hi, I'm Prof and welcome to Chemistry Matters. Today we're going to be talking about a thing called atomic emission. We're going to start with a little history lesson, as we often do, and we're going to go back to the late 19th century, and quite a few physicists sort of thinking that science was coming to an end because they could pretty much explain everything. Certainly in physics anyway, this was more the physicists who were saying this. There were only really a couple of things that they couldn't explain, and one of those was this process that's called atomic emission. And that occurs when you take an atom, you excite it, and you can excite it by giving it energy somehow. And it can absorb that energy, and then it needs to get rid of it because it's now got too much. And one of the ways in which it can get rid of energy is by emitting it as light, or as photons of light, let's say. And basically the physicists couldn't understand the way that this worked, and they thought once we get this sorted out, we'll be able to explain everything, and science will be at an end. Boy, were they wrong, because this process that we're talking about basically ushered in this thing called quantum mechanics that many of you may have heard of. And that is the way that we now understand, I guess, the atomic world. So anyway, what are we talking about here? Here is a little diagram of an experimental setup for looking at atomic emission. So here we've got our sample in a gas discharge tube, so it's in the gas phase. We are putting a potential difference over that, very, very, very high voltage. And what happens is that the gas glows. And it glows. As it glows, it's giving off energy as light. And we put that light through a slit. We then put that light through a prism, and what we find is that the prism takes the light and splits it into its components. And what we find is that when atoms emit light, they don't emit any old wavelengths of light. They emit certain definite wavelengths of light. So we can see in these diagrams here, for example, hydrogen, an excited state hydrogen atom will emit radiation of only 4 colors. Bam, 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 those 4 colors there. For example, a neon light, and we've all heard of neon lights, if you take neon atoms and excite them, you get an emission spectrum. Again, it consists of a series of discrete lines, but these discrete lines are more sort of in the red region of the spectrum, around about 700 nanometers, and that's why neon lights are those beautiful red-orange color that we see. Sodium lights, for example, the street lights that you see, they are generally sodium lights, and they are orange-yellow, and that's because sodium atoms emit orange-yellow radiation, etc., etc. The physicists couldn't explain how this all worked. They didn't understand why atoms only emitted these particular wavelengths of light. And it took a great scientific genius, we'll call him that, by the name of Max Planck. He came along and said that atoms could only emit certain definite energies of light, or certain definite wavelengths of light, because atoms could only have certain definite energies themselves. They couldn't have any energy that they wanted. In other words, energy on the atomic scale was not continuous. And that, as I mentioned before, was the basis of this thing called quantum mechanics, because Planck came along and said that atoms would emit quanta of energy, okay? Only particular values of energies of photons. That's the visible light that we see when atoms emit energy. We could use an analogy here to, let's say, a ball on a staircase. And we could say, okay, if we've got a ball on a staircase, it can only have certain particular energies. A ball on a staircase can only be resting on a particular stair on a staircase, can't it? Okay? It can't exist between 2 stairs. It can only sit on each particular stair. So, a ball on a staircase can only drop down in energy in particular amounts, and that corresponds to the stairs. Okay? So it could go from the 5th stair to the 4th stair, or down to the 3rd stair, or the 2nd stair, or whatever, but it can't go, for example, to the 2.5 stair. And atoms are kind of like that as well. atoms can only exist in particular energy levels. So here would be an energy level diagram for any old particular atom. And that atom could have this energy, or this energy, or this, or this, or this. But it couldn't have this energy here, or this energy here. It couldn't be between these energy levels. So when an atom is changing energy by either gaining energy or losing energy, it can only do it in certain discrete amounts. And we call these quanta. So one way of exciting an atom is for it to absorb a photon. And it can absorb a photon. A photon has energy, and so that is going to excite the atom, or more specifically, it's going to excite the electron in an atom, and it's going to take that atom from, let's say, the very lowest energy state up to, let's say, the fifth energy state. Now, in order to do that, that photon's got to have that particular energy and no other, because that energy difference there corresponds to the difference in energy between the fifth state and the first state, okay? So it can only absorb photons of a particular energy. In other words, that's quantized. And then once it's got to here and it wants to get back down, it can only do it in discrete steps. It can only emit photons of particular energy, corresponding to it jumping down from here to, let's say, the fourth level, or from the fifth level to the third level, okay, in particular steps. So that is the explanation of why the atomic emission spectra look like this. They look like discrete lines. Each of these lines corresponds to a transition of the atom from a certain definite energy level here to a certain definite energy level there. Okay, so that's the way that we understand what's going on when atoms either absorb energy or emit energy. They do it in certain discrete steps. Okay, so let's have a look now at some examples of what's going on, and let's do some calculations here, okay? So we can quantify what's going on here now through using this equation here, minus 2.18 times 10 to the minus 18 joules divided by n squared. So this equation tells us what the energy of any energy level in a hydrogen atom is. Okay, and the n is any integer. So n could equal 1, 2, 3, going all the way to, if we really want to, infinity. This equation allows us to calculate any energy level that we want, corresponding to the value of n, where n is 1, or 2, or 3, etc., etc., etc. So let's do an example. Let's say we've got a hydrogen atom, and it is in the n equals 4 excited state. And we want to calculate now what the wavelength of the photon is going to be if it goes down to the n is equal to 2 state. Okay, so how do we go about that? Well, there are a couple of equations that we're going to use. We're certainly going to use this equation here, and we're going to use this equation here as well, which you may or may not have seen before. E is equal to hc upon lambda. So E is energy, lambda is wavelength, H and C perhaps you might not be too familiar with. And so H is a thing called Planck's constant, named after the man himself, and that equals 6.626 times 10 to the minus 34 joule seconds. And C is equal to the speed of light, and that is equal to 3.00 times 10 to the 8 meters per second. Let's now utilize all of this and solve this particular problem. The question says, right, we've got an H atom in the n equals 4 state. It's going to pop down to the n equals 2 state. What's the wavelength of the photon that gets emitted when it does that? Okay, and so now we're going to use all of this to solve this problem. We've got an excited state hydrogen atom in the n equals 4 level. It's going to drop down to n equals 2. What's the wavelength of the photon that gets emitted when that happens? Okay, so the first thing that we're going to do is to calculate both E4, the energy level of the energy of the fourth level, and E2. So E4 is going to be minus 2.18 times 10 to the minus 18 joules over n squared. N, remember, is this number here, 4. okay? Very common mistake in these sorts of calculations, people forget to square their n. So that's going to be over 16, and that is minus 1.36 times 10 to the minus 19 joules. Okay, E2, the energy of the final level, is minus 2.18 times 10 to the minus 18 joules over 2 squared, which is equal to 4, and that equals minus 5.45 times 10 to the minus 19 joules. Okay, so we've got those two energy levels, okay? Here is E4 here, and here is E2 here. This is what's happening. We're going from E4 down to E2. Okay, we know the energy of that now. We know the energy of this. We want the difference in energy, delta E, between those two. So delta E, in this case, is going to be E2, because E2 is the final energy, minus E4. And again, if we do the calculation, that comes out at minus 4.09 times 10 to the minus 19 joules. Okay, so we are nearly there. We've calculated that energy difference. That's the first part of the problem solved. And now the second part, remember, we're asked, what is the wavelength? Okay, what's the wavelength of that photon that gets kicked out? Well, in order to do that, we're going to use the other equation. So E is equal to hc over lambda. Okay, E is equal to hc over lambda. We know what E is now. We've calculated this. It's this number here. We know what h is, that's a constant. We know what c is, that's a constant. We want to find what lambda is, the wavelength. So lambda is equal to hc upon E. So that's our rearranged equation. And so let's write out this, let's do the calculation. So what have we got? We've got lambda is equal to hc upon E. So h from earlier in the video, 6.626 times 10 to the minus 34 joule seconds, multiplied by the speed of light, 3.00 times 10 to the 8 meters per second, all over the energy difference between the two levels, and we calculated that down here, okay? Now notice we've got a negative sign here. We can dispense with that because all that we're talking about here is an energy difference, okay? And the reason that we dispense, well, if we don't dispense with that, we get a negative wavelength, which makes no sense. So we're going to get rid of that negative sign, and we're just going to say over 4.09 times 10 to the minus 19 joules. Now, let's look at our units and make sure that we've rearranged the equation correctly, because what we're after is a wavelength. Wavelength has units of meters, so this whole thing here should have units of meters. So, does it? Let's go through and cancel everything out that can be cancelled out. Joules gets cancelled out with joules, that's gone. Seconds and an inverse second, a second to the minus 1, they're going to cancel out. What are we left with in terms of units? We're left with meters. That's all good, okay? So that means that we must have rearranged the equation correctly. And so if we go through, put that in the calculator. I urge you to do this, follow through yourself, make sure you can use your calculator properly. You go through and do that, and the answer that you're going to get is 4.86 times 10 to the minus 7 meters. Or in the normal sort of chemistry speak, we would say that that is equal to 486 nanometers. 486 times 10 to the minus 9 meters, okay? So that then is the wavelength of the photon that's going to be emitted when we take a hydrogen atom in the n equals 4 state and we let it drop down to the n equals 2 state. So that's the general way that you're going to do these sorts of calculations. The first thing you're going to do is to calculate the energy of the starting state, the energy of the final state. You're then going to get the energy difference between those two by subtracting them. And then you're going to be using this equation, E equals hc upon lambda. You're going to rearrange that to make lambda the subject and plug in all of your numbers. Remember, you're always going to be given these constants here. H, Planck's constant. You don't have to remember that it's 6.626 times 10 to the minus 34 joule seconds. I'm meant to know that, but you guys aren't. You'll always be given that in an exam. Same with the speed of light. Okay, so don't go learning constants. You'll be okay. And so there we go. that's your big calculation, 486 nanometers in this case. There's only a certain number of problems that can be asked in this case. For the visible lines of the hydrogen atom, you're going either from 3 to 2, 4 to 2, 5 to 2, or 6 to 2. So that gives you 4 possible problems that you can do here. So basically practice them all. One of them will come up in the exam. Okay, I hope you've learned something today, and we'll see you next time.